Hi, today I would like to do my presentation on my ICASSP paper titled Deep Neural Network-Based Matrix Completion for Internet of Things Network Localization. This paper was written by me, and my name is Sun Kim. The two other authors who contributed to this paper are Loom Trung Nguyen and Professor Byung-Hyun Shi. Also, before I start my presentation, I would like to thank the ICASSP 2020 and its committee for giving me such a wonderful opportunity to give my presentation at this world level top signal processing conference. Okay, so first I would like to discuss my problem model, and then I would like to discuss some of the conventional alternating minimization techniques followed up with my proposed technique, and I would like to end my presentation with my simulation results. Okay, so in recent years, Internet of Things has received significant attention due to its variety of applications such as surveillance, communication, and also environmental monitoring and such. In collecting the environmental data such as temperature, pressure, humidity, wireless sensor network has been popularly used. In this network, there is a large number of sensor devices, and in our scenario, we have n sensor nodes in the k-dimensional Euclidean space. So we can have sensor nodes in 2-dimensional or 3-dimensional Euclidean space. And in order to make appropriate decisions to the collected environmental data, such as emergency request or fire alarm, the data center must identify the full pairwise location, distance location between each sensor pair. So sensor nodes measure the distances to the other sensor nodes. We would like to see some mathematical formulation of this problem. Xi means indicate the original locations of sensor nodes. Dij is the pairwise distance between xi and xj. And here is the Euclidean distance matrix that we obtained at the data center. And our problem is to use this Euclidean distance matrix to compute x. And the way how we do it is by taking the eigen decomposition of this matrix D to compute x as shown in this equation. But we do have a problem in our setting. The issue is that only partial distance information is available. So, which this means that not all the distances between each sensor pair is measured, which means that we have some of the missing entries in our observed distance matrix. And this is due to various reasons such as the power outage of sensor nodes, limitation of radio communication range, and sensor node being located at the blind spot. So since there are many unknown pairwise distance entries in the observed distance matrix, one has to recover the original Euclidean distance matrix from a subset of entries. So as you can see, we're trying to recover the missing entries of matrix D, and we can see that we can formulate this problem as matrix completion problem. Additionally, when n sensor nodes are distributed in k-dimensional Euclidean space, then the rank of this matrix is at maximum of k plus 2. So we can have the most possible maximum rank of D that we can have is 5, 3 plus 2. And here's the way how and because this D is a low rank matrix, and thereby we can solve this problem using a low rank matrix problem. And this is the mathematical formulation of our problem model. And here, as you can see, E is the index set of observed entries. Where in our case, R is the communication range. And Most importantly, note that this problem is the least square minimization problem. The least square minimization problem is highly robust to observation error and noise, and computationally less burdensome compared to the rank minimization problem. Rank minimization problem is just another way of solving it, but as you can see, the least square minimization problem is a lot more beneficial. Many different approaches have been proposed to solve this least square minimization problem. In solving our problem, alternating minimization scheme has been popularly used. In alternating minimization schemes, matrix X, Y, and D are computed in an alternating fashion, which means that first we would like to update variable X in the ith iteration as the following. And then once we update variable X, then we can similarly update Y and then D in the following order, while fixing others at their updated values. And in solving each subproblem, like trying to update X, various alternating least square techniques have been suggested, such as the following. And we would like to take a look at how these algorithms work. So in least square techniques, we obtain the new iterate X by using the least square method. And we can see that we use the matrix, we try to calculate the matrix multiplication of these two variables. And similarly, similarly, we can update variable Y and variable D by using the pseudo-inverse of a matrix. And the alternating minimization techniques repeat these procedures until the objective function reaches a user pre-specified tolerance level, so that we can terminate the algorithm when that actually happens. The real main problem in IoT networks is to identify the location of sensor nodes from partially observed distance information contaminated with Gaussian and Laplacian noise. Fortunately, many of these alternating least square techniques have proven to be successful even in the presence of Gaussian noise, but when Laplacian noise exists, which is well known for modeling outliers in many practical scenarios, there are a lack of contributions that in these alternating least square techniques that deal with Laplacian noise. So therefore, it is very important to come up with some new recovery algorithm to deal with both Gaussian and Laplacian noise in this procedure. So here's our proposed technique. From the definition of pairwise distance, we can see the relationship between the sensor location matrix X and the Euclidean distance matrix D. We can use the function g, and we obtain this function g from the pairwise distance definition, as I mentioned. And one important thing to note is that when the nodes are randomly distributed in k-dimensional space, the rank of this coordinate matrix or sensor location matrix X is k almost surely. Using this useful facts, we can modify the objective function as the following. And as you can see, we try to find the solution of the optimization problem on the feasible set X, as stated here. Okay, so we propose a novel Euclidean distance matrix completion approach to detect the location of sensors in both Gaussian and Laplacian noisy scenarios. For an efficient and highly accurate low-rank matrix completion from the distance measurements, we exploit the deep neural network. It is now very well known that the DNN is highly efficient in learning a complicated nonlinear function, and it has been applied to various applications such as image classification and machine translation, and just to name a few. In our approach, DNN is particularly used to recover the node location matrix X from the noisy observed matrix DO. Henceforth, our proposed LRMC scheme MDNNL is trained such that it recovers the entries of the sensor location matrix X using the information from the noisy observed matrix D in an unsupervised fashion. Okay, so since we adopt an automated minimization approach, we are trying to solve X and D by dividing the main problem into two subproblems. First, we would like to solve subproblem 1, and then we follow up with subproblem 2, and in this way we can solve XD iteratively. In our proposed technique, we try to solve subproblem 1 by employing multiple sequentially cascaded DNNs. Here, we try to compute X using the ith DNN in the ith iteration. So here, we try to use one DNN to solve each subproblem in one iteration. And then we try to solve subproblem 2. As you can see, we are able to optimize each entry of D, and we're trying to compute D using a slightly modified version of update expression of D in the previous alternating least square technique. So we obtain this expression, and we can rewrite this expression in a more intuitive way, as shown here. So here's the detailed architecture of the proposed MDNNL. As you can see, each DNN is trying to solve the subproblem 1 in the first iteration, and here this DNN is trying to solve the subproblem 1 in the ith iteration, and here this DNN tries to solve the subproblem 1 in the last iteration of our entire problem. So for the choice of DNN, we specifically use the autoencoder to predict X while preserving the rank, the size and low rank structure of this reconstructed matrix. And so we can actually use to predict the unlabeled X by using an autoencoder. So in our training, we use the autograd optimizer, which adjusts the learning rate eta for each parameter, and this optimizer is especially suitable in our method, as it yields fast and accurate optimization and relieves the pain of manually tuning the learning rate eta. So we would like to briefly look at the simulation results. We use the mean square error as our performance matrix, and in measuring the performance of each algorithm, we perform 1,000 independent trials to compute the average MEC. Here's the noiseless scenario of our proposed technique in comparison to the state-of-the-art of other LRMC algorithms. As you can see, our proposed technique outperforms all other algorithms, and also in the noisy scenario where sampling ratio is fixed to 0.6, we see that our algorithm outperforms all the other algorithms, even in high SNR regime. Why does our proposed method outperform the conventional techniques? Well, conventional techniques are trying to solve the LRMC problem using the low rank constraint. But in our proposed method, we try to exploit the low rank constraint on top of the positive semi-definite structure of the matrix D. And henceforth, we can obtain very good performance of our proposed technique in comparison with other algorithms. Thank you so much, and that is my presentation.